You don't need all those annoying sounds. Okay, do I have everyone's homework assignment? Oh my gosh. Hey, quick question. If this little, are you able, for those of you who have the meeting up, are you able to see I'm writing on the screen? All right, I just want to make sure that was right. Okay. So thanks for bearing with me. I got dragged into a meeting at the very last minute, but made sure to make sure I was here. We have everyone's homework assignment. I will have all the homework assignments back to you by this coming Monday. So the material that would be covered on the take-home exam will be through Wednesday. The material that's covered next Monday, hold on to your TGOs because obviously you're going to want to be able to do the assignment. So I'll reiterate that so that way you can just turn them in with your exam the following Monday. So does anybody have any questions on anything we've covered so far? So we've kind of, up to this point, we've kind of alluded to this idea of delay. That because there's an actual physical quantum response, electrons are excited due to thermal vibrations. You put a voltage on a gate, it's pushed down, you hit the threshold voltage, you've created an inversion layer, which then allows the conduction through the channel, right? And so these equations that we derive that relate to the drain source current all relate to the oxide thickness, the mobility of electrons, the gate capacitances, your leakage currents, all of these different things that you have to worry about, band-to-band tunneling, body effect, all these issues eventually tie in to the fact that when you want to turn on a transistor, it takes a certain amount of time. And so these issues are known as delay and transient response. So that's what we're going to be covering in section 3. And your first lab in the last 3 weeks will deal specifically with how do you design a circuit and deal with delay and transient response. So these definitions, I don't require you to draw the diagram, but it may be very good for you to understand how the diagram works in relationship. So from here on out, you're going to see a lot of rise, TPDR, TPDF, TPD, TR, and TF. So what I mean by that is rising propagation delay. So from the input to to rising output, crossing half of VDD over 2. So if you have some sort of rising propagation delay, you insert an input to rising output. So here you've created some sort of input and you get to half of VDD on the input, right? And so then what's going to happen is you have some sort of logic on the output. In this case, it's actually inverting. So it's logic 1 to logic 1. Something changes. So at this moment it changes. And then it takes from here to this point to get to half of the output supply voltage. The distance between that time, the time between when this occurs and when you reach half of the VDD on the output is the same thing. If it was logic 0 and this was going to a 0, 1, and this was a 2-input AND gate, and this VN created your second output to be a logic 1, and it was going like this, and you hit like that, that would be your same thing. So falling propagation delay. So to falling output, so this is sorry, this is TBDR, this is TPDF, falling. That means this output is falling, this output is rising. So this is R and F. Now those aren't always going to be the same, as we're going to be learning a lot in this section and the next section, because it depends on the sizing of your PMOS and NMOS transistors. So in the fundamental, the relationship between your PMOS and NMOS is 2, because the mobility of electrons is assumed to be twice as much as mobility of holes. So as a result, we have to size these transistors differently. And what we're going to learn is as we put a load on them, and you have to account for gate capacitance, this result is these rise and fall times are not going to be the same always. You want to design the transistors so they're as close as possible, but you may have a slight difference between them. And as a result, you're often going to actually try to calculate this average. So that's a third unit, TPD, propagation delay of average. So that's just your rise plus the fall divided by 2, just a standard average calculation. And you can actually, when we learn about SPICE, you can actually use this to calculate. You can actually use your simulator to monitor when you're, at what point it's a specific node in your circuit. You say, okay, this output node, this portion of the transistor, I want to know when it reaches specific rise and fall time. So you can actually write in code that says, when you have the input node, which I defined as this, is rising and reaches VDD, at that time start, and then you have the other node, which is fall, give me that time start. And then the difference between those two times is going to be your false time propagation delay. You calculate the same thing for falling, and then you can add them together. And then in your transient analysis output file, it'll actually have all of those. So you can actually use those to calculate the exact values. And you can go, okay, well, maybe I want to design the transistor size a little differently. And then you can use Monte Carlo analysis to figure out what your optimal average propagation delay. So if you're trying to optimize it so it's as close to 0 as possible, you get the output, you sort the output table, give me the smallest one, and then you tie that into your transistor size. And then that becomes the transistor size of the cell. And so you'll see these defined in different places, but the textbook uses 0.2 to 0.8. So it's this range to this range we talked about. Our regions here. So we have our, if we have VIL and VOL, right? VIH and VOH as we calculated last time. And ideally you want it to be able to, ideally you'd want it to go from 0 to 1 every time, right? So you get some sort of transient response and then it goes to 1. But that's not always going to be the case because we live in the real world. So the key thing is, if you're not getting from 0.2 to 0.8, you need to resize your transistor immediately. If you are, you can actually use buffers. Oftentimes buffers are used to restore the signal. So if you're getting from 0.2 to 0.8, right? So you're in this range here, and it goes through a buffer, you can size it in such a way that it will actually go to 1 and to 0 again. And that's a very common design technique. And so we'll learn a lot about that later, but that's kind of why you want to, this is where your trade-off between size and signal integrity is important. Because before that, you're just worried about getting to logic 0 and logic 1 and putting these AND gates and OR gates. But now you have to worry about the size of the gates, any buffers you have to put in to ensure that all the signals get to at the end of the bus at the exact same time. You also have to worry about signal integrity. So that's where your good design requires good compromise comes into play. Okay, so timing basics. So T0 3.2 is just this. A timing analyzer, which is kind of what I was just describing to you, computes the latest time at which each node in a block of logic will switch. And so these other three terms here are going to become very important. You're going to use these over and over again throughout the rest of your course. Slack, contamination delay, and the critical path. Critical path, I think all of you are familiar with at some level. Right, so critical would mean, other than the fact that I have critical path design defined as the path of the entire design with the maximum delay. Why do you think that's important?
Max amount of time it will take.
For what? You're on the right path. Pretend you're in a job interview. Why is critical path important?
Trying to remember what city. I guess so you know, kind of like a critical point. You need to know like what your maximum is, so you know you can prepare for the entire.
Bingo. See, you did know it. The critical path, you have a certain amount of logic, right? And you're going to have a number of different outputs. So let's say you're calculating you're designing an adder, right? So you have your sum and your carry out. Now, oftentimes you have a 1-bit adder and you're going to be tying it into a 32-bit adder. You're going to have a carry look ahead or carry select or ripple carry adders, right? So when you're dealing with those kinds of adders, timing is paramount. You have to really care about that. So in most cases, your critical path is going to be your sum, because you have, your carry out, because the sum is just 3 XOR gates, right? But you have to worry about OR gates and AND gates and another OR gate. And when you're dealing with that kind of design, you have to worry about a number of different things to get to this critical path. So you want your sum and carry out to get out at the exact same time. And so that's why that's what Bo was just saying, is that we have to know the maximum value, so that way we can account with the buffers on the non-maximum values. So to account for that, we worry about this concept of slack. Slack is the distance between the required time and the arrival times. So especially when we get into section 6, we're going to be dealing with slack in a lot more detail. But positive slack is what Bo just described. It means that the circuit meets your timing constraint. I need it to get to this point in the circuit at a certain time. I don't want you don't want to be rushing your circuit, right? Especially when you're dealing with sequential elements. Sequential elements and timing is very important. Negative slack means your circuit is not fast enough, meaning that you need it to get here at this time. You need the switch to occur by the time you get there, right? If you have negative slack, then you have some sort of TPDF, which occurs too late. And the reason why you may need this is, if you're dealing with an SRAM circuit and you worry about word line and bit line, and you need to sample at specific times, that means your clock signal is going to dictate when it's sampled. So if you have negative slack in your circuit, that means you're going to be sampling an incorrect value. So this term for slack, what other terms have you heard in 385 or 285 or 235 that for negative slack? It starts with an R.
Recursion?
No, recursion is what happens when you're trying reaccessing a function. Like if you have a circuit and it's being accessed before the timing before it's ready, what is that called? Starts with an R, it's 2 words, RC. The second word is a C. Second word is condition.
Race conditions.
Race conditions, right? So negative slack is a description of a race condition. Okay. The reason I did that is because especially for those of you who were at my resume thing yesterday, a lot of times you have to understand that just because you know one term doesn't necessarily mean the HR lady who's looking over your resume knows that term. So oftentimes it's good to know when there's multiple terms floating around which essentially mean the same thing. So in this case, if you have a race condition in your circuit, one of the main causes is this negative slack. So the reason why I'm going to be doing the exam the way that I'm doing, where I'm having it simulate a job interview, not just because I want you all to get kick-ass jobs once you graduate, but I want you all to kind of start putting together pieces from your other classes. Start thinking like, oh, that thing that I learned in microprocessors, oh, or that thing I learned in 385, oh, it shouldn't just, I know it's an exam and I have to give exams in order to meet AVET accreditation, but I also kind of want it to be a realization that all this hard work you've put in for the last 3 years and 4 years is starting to click together. So that's why I'm kind of asking the questions the way that I am. So, race condition, there you go. So does everybody have, everybody's writing it down, does everybody have 3, 4, and 5? The contamination, I should talk about contamination delay. The minimum amount of time from when an input changes until any output starts to change on its value. So tying in what Bo was saying about race, not race conditions, critical path. So you have your 1-bit adder, you have A, B, and carry in, right? So once you change one of the inputs, you're going to get an output change. And we're going to study a lot about this in contamination delay in the labs. That you're going to find, especially when you're doing with 2-bit AND gates, that you change one of the inputs from a 0 to a 1 or a 1 to a 0, the time it takes to change is different. And you have to worry about all the different combinations because you have to worry about pull up and pull down networks. You know, when you have, for example, let's say you have your AND gate, right? Let's see if I can just draw it out with this. Okay, so you have your 2-input AND gate, or this is a NAND gate. So let's think about this on the logical level, right? So we have our gate, source, and drain. So this is drain, source, gate, right? So I have a change that comes in on this input here, right? Sorry, Josh, I just spilled. It's okay. It's a morning. It happens. So anyway, I changed the A input on the gate, right? I have 3 transistors tied to the same drain. So if I change this input and this input, as opposed to this input and this input, based on your transistor sizing, you might get different changes on this output. So if you have, it's a NAND gate, so I want to do, let's say I have a 1, 1 here, right? So if I put in a 1, 1, you're going to have a 0 on the output. You're actually, based on your transistor sizing, changing this to a 0 is going to change this to a 1 at a different timing than this one will be. Because this one's already tied to the drain, whereas this one is not tied to the drain. You have to worry about the other transistor. So that ties into this 3.4, this contamination delay concept. Okay. Does anybody have any questions before I move on? All right, okay, so here we go. This example question is a really good, so this little mini algorithm I came up with here to calculate the maximum delay. Start at the nodes, at the gates on the left, add the delay to the longest input delay. So, example 3.1, identify the critical path. What is the minimum amount of slack required for proper circuit operation? And how would you modify the circuit to ensure both outputs of the circuit output at the same time? So we have, let me scroll down because part A, the solution is here. So here's what you do. You get this kind of circuit, and you start out here. These are the input delays, right? So you would calculate this out. So in this case, it's 20. The delay of this specific NAND gate is 30. So if I was going this way, right? At each node, you have to we want to calculate the maximum delay. So this value A7 is equal to 60. what that's saying is here it's 30, here it's 30, goes to 30, it's 90, and then gets to 140. So that's going to be your critical path. So in this case, if it's 50, it's going through 30, it's going through 110. So what this means is you take the maximum value of your inputs and you look at this gate here, right? So A0 and A1 are the two inputs here. So A1 is 30, so you take the maximum value and put that node value here. So if we were doing this, we do 20 and 30. We go, this one's bigger, so we put 60 here. Does that make sense? So we're trying to find the maximum value, so that's 60. Same thing, this is 20 and 60. Well, 60 is bigger than 20, so we're going to go 90 here. So here the inputs are 20, 90, and so this is 20 and 20, so they're the same, so this is 40, so this becomes 60. So our three inputs here are 90, 20, and 60. So the biggest one's 90, so this is going to become 140. Here we have 50. We can make this 80. So 50 and 80. 80 is the largest one, so this becomes 110. Does that make sense? So then we go, okay, well, there's my critical path. So in order for the circuit to work, the minimum amount of slack is 140. But now I have this condition here where this signal gets there 30 seconds before this one does. Okay. So the solution is just add a buffer here with a 30 nanosecond delay. And then guess what? Now they're both getting out at 140. So that minimum amount of slack ties into your critical path. So in this case, what we're doing is we actually design a cell where we have 6 inputs and 2 outputs. And then after you do that, you just know that, okay, the delay of this cell is 140 nanoseconds and the outputs of both are coming out at the same time. So it's the same thing we're doing here. We've sized a NAND gate somehow, have 30 nanosecond delay. This inverter has a 20 nanosecond delay. So all of these are the same unit cell. So this NAND gate, NOR gate's 40. Now, you see this, we'll get into more details as to why this is. But you see this NOR gate here is 40 and this other one is 50. That has a lot to do with your input and output, especially dealing with capacitance. Because your input here is just 2 wires, right? Well, now you have the drain from 3 transistors tied together, tied to this input, and the drain from 3 transistors from this input tied to this input, right? So you have a lot of input capacitance you're dealing with. So as a result, you're going to make the size of the cell bigger so that way you can ensure that the transistor is actually switching and getting from your low region to your high region properly. So that's why this one and this one would be different.
Okay, is 30 nanoseconds like the standard?
No, this is just a specific circuit.
Okay.
Yeah.
Is that critical path, is it jumping from the top to the next line, or is there actually a...
No, there's here it is. So it starts here at this input. It goes through this NAND gate, and then goes through this NAND gate, and then goes through this 3-input NOR gate.
Is there a standard for like how long it takes to go through a certain gate? Or
No, because as you guys will learn, everything has different transistor sizes, features, so there's no standard time.
Okay. So if we were doing like the whole thing, this is down up transistor level, we'd have to find 0 and 1 also find the critical path, like 15 say they were different somehow.
Mm-hmm.
You're
regarding the positive and negative slack, like your 140 would be your positive slack, and then the
Yes.
190 would be your negative slack.
Yes. So that's why you have to put the buffer on this to make it work. Any other questions? All right, see you in a second. So that just, okay, so that paragraph's just kind of me describing everything we just talked about. So transient analysis is a measure on the impact of the output voltage if Vn changes. So we're having them as functions. So we are analyzing now what happens when I put in an input function, like so. What happens here? And we call that transient analysis. And the reason we use the word transient is because we have some sort of input signal, which is causing some sort of output signal. And that's our transient. That is transient here. That's what that word means. And so we want to figure out, y'all probably remember the derived equation here. If you remember this from, I think it was section 2, we talked about how the current is equal to the capacitance times the rate of change of the voltage over time. So now we can relate here, we have some sort of unit step response times our supply voltage. So this is U of TO minus T, right? So that basically allows us to determine if it's 0, right? This relates to how our output changes. So sometimes when you have VDD as 1, but you want your output to be 0, that's where this UT minus T0 comes in. For those of you, I know it's like 9:30 in the morning, but I'm starting to have you think back to Calc 1, step responses and how that all works. Especially those of you who want to do really well in control theory. Yeah. So being able to relate the current and your load capacitance to the rate of change of your output allows us to be able to derive a transient analysis of our step response to the circuit. And now we take our topical guide objective here where we related IDS, right? So our current was from drain to source of our NMOS transistor. We relate that to the rate of change of the output voltage times 1 over CL, right? Because I over CL is equal to the rate of change of voltage. So you just multiply CL and CL, right? Multiply by that, you get your rate of change. And that gives you our current. So now we now have a relationship between our load capacitance, our rate of change of our V out, and the current in linear cutoff and saturation modes. And so VNA, I have a little thing you can kind of go back there and check out that link. I know you have it already, but you can go there. It's a source follower circuit. So while I don't have that as a topical guide objective, that could be a really interesting exam type question. So I have a circuit here and I want to relate the drain source current to the rate of change of voltage. So tell me how to derive the solution and prove that part. So how would you go about solving such a problem? I'd say the first thing you'd want to do is say, okay, I know the drain source current. I know that there's some way of relating it, that I have this IDS is equal to the load capacitance of dV over dt, right? Now, I know from previous proof how we came up with our linear cutoff and saturation currents, right? So then what I would like to do is go, okay, well, put these in there. I can then tie it into the step response. And then we know that here, before we reach T0, we are in cutoff. We have not switched yet. And then once we hit this cutoff range, so now we're starting to get in this transient response, our output voltage is going to be less than the VDD minus your threshold voltage, right? And then, it's the same. It should be different. Okay, so once we actually exceed the threshold voltage, you're actually going to get to your actual saturation region, right? So saturation region is when we have those differences between the threshold voltage and your drain and source. So you're having that your drain voltage is increasing, so VDS is increasing. This equation doesn't look right. I will go back and I think it should be the other way around, where the VDS minus VDT. That's the case. So okay, so delay estimation. So up to this point, we talked about, well, okay, so we know that there's delay, we know there's this physics, and we know that there's these step responses, and we know that we have to account for positive and negative slack. But how do we, as George was just asking, figure out the exact actual model? So you've probably known from circuits or other classes that when you're dealing with RC responses, you recall, like, you have your time delay and you have some sort of rise like this, and eventually, and usually it's 5 RC step response when you're dealing with an RC circuit, as you recall. So now we're going to talk about this concept of effective resistance of a transistor. So we know it's not a resistor, but we do know the voltage difference between the drain and source, right? And we know that there's current going through the transistor in a given moment. So if we have a voltage potential and we have a current, then we just are able to calculate this effective resistance. How long does it take for a charge carrier to get from the source to the drain? And then it's during this specific switching interval, so I only have to worry about switching. So 3.7, so I can scroll down here. Oop, too far. Is the ratio of the drain source voltage and IDS across the desired switching interval. So now we start out in cutoff, right? And then as we're switching, we're trying to get to this point where we can actually get to the linear mode, right? So we have to worry about step response, what's actually going on here. So we have this IDS, which we've calculated, and we have this drain source voltage, which can be measured. And as a result, that just by using Ohm's law, that allows us to calculate the effective resistance of the circuit. Okay, so RC delay model, we're going to be learning a lot more about this. This is where you start tying everything in. So the PMOS is typically going to have 2R as opposed to a typical NMOS transistor. And that's just because we're sizing the transistor width in order to be able to account for the mobility of holes and electrons. And so resistance is inversely proportional to width. Only switching capacitances are relevant to the delay. So the reason why I've highlighted this is because if you have a 2-input AND gate, right? 2-input NAND gate. So I have one input here, and I tied it into this NMOS transistor. And I'm not worried about these other two transistors, right? This one's not switching, and this one's not switching. They stay the same. And so I currently have a 1-1 on both of the inputs. And I'm going to switch this one to 0. That means I've changed the output from a 0 to a 1. So that means this transistor is switching and this transistor is switching, but the other two are not. So you have all these gate capacitances and internal capacitances of these transistors, but only the switching capacitances are relevant to the delay of the circuit. So we're going to start taking in our models of our NMOS and PMOS transistors and start actually using this to determine an RC model. So this is 3.8 here. And the general idea is that we have our gain, source, or drain of our NMOS transistor. So the one on the left is the NMOS, and the one on the right, as you probably all can figure out from the bubble, is the PMOS. So we have our input capacitance and an output capacitance. And here in this model, we're actually treating the transistor like a switch, but then accounting for the actual reality by accounting for resistance and capacitance. So the reason why, so let me ask you this question. So we have a capacitor here, capacitor here, capacitor here, and we have capacitors on the gate, source, and the drain. Why do you think capacitance is on all three of them? Going back to the physical model of the transistor. Right, so you can find the current, but why do you think specifically the model is saying, like, we're going to have a resistance from the drain, the source, but I don't have a resistor on the gate, I don't have a resistor on the source, but I have capacitances at each of them. So what I'm asking is, why is there a resistor here, and why is there a resistor here in the PMOS, but I don't have a resistor here, but I do have capacitances there, there, and there? Same thing with the NMOS. Why do you think I have separate capacitances? Think back to your transistor model. So here is your SiO2, you have gate, and you have a bulk, and you have doped source and drain, right?
Does the resistance represent the width and length?
Yes, because it ultimately represents the current. So we have IDS, right? So that's going to be going here. But what are each of these capacitances dealing with? What is capacitance?
Storage.
Yeah, you can store charge, right? And how does it store charge? Potential, and how is that potential done? Yeah, so tie in this idea of plates to your transistor model. You have some sort of, we were talking about body effect and we were talking about design issues. So you're going to have some sort of capacitance at your drain, source, and gate. And they're all separate because they're all separate in your actual physical model. So you're going to account for that here, you're going to account for that here, and you're going to account for that here. The resistance is going to represent your effective resistance, which we calculated as VDS over IDS. So our effective. And so the difference between the NMOS and PMOS model is that you've just doubled the resistance. Okay, so this is my little algorithm that I came up with to try to come up with to develop the RC delay model for the circuit. So for each PMOS path, so let's say we have a NAND gate here. So for each PMOS, set K equal to 2 times the number of PMOS transistors the current must flow through. So that, remember that I had that value that K comes the capacitance. So in this case, it's 2. For each NMOS path, set K equal to the number of NMOS transistors the current must flow through. So it flows through 2. Here it flows through 1. So K will be 1, 1, and 2. So if this were a 3-input NAND gate, you'd put the third transistor here. And I'm sorry, this would be 2. I'm sorry, because it's 2 times. So this would be 2. And this would become 3 because we're going to be adding a third NMOS transistor. You see what I'm saying? So those first 2 steps. Then substitute the transistors with the equivalent RC circuits, so the same ones from 3.8. Right? So then you say, okay, so I've set these K values for each path. And then I'm going to take that TGO, plug it in, and then determine which capacitances contribute when the output is switching. So recall that resistors add in series and capacitors add in parallel. And therefore, we're able to compute the input capacitance for each input by adding the non-switching capacitances. So what does this mean? We figure out specifically, so we have 0, 0, 0, 1, 1, 0, and 1, 1, 1, 1, 1, and 0. So for each case, what's happening is the capacitance occurs when one of the inputs switches to a 0, right? So either both of them are going to switch at the same time here, to switch from a 0 to a 1 on the output, or if one of them switches, you're going to get a 1 to switch on the output, right? But if you're switching this one, that means you're not switching this one. So your capacitance changes by which transistor you're switching. As a result, that's why you're going to get different rise and fall propagation delays based on certain changes, because you're having different capacitances and different drain source currents contributing to the actual switch. And then the last step, if my mouse ever shows up again, compute the original capacitance for all the capacitances at the output node. So we're going to do a couple of examples to show how this occurs at each step. Oh. That is my attempt to make this process easier. Yep. Before I go on to the example, does anybody have any questions? I know that once we go through example 3.9 should make a lot more sense. All right. So here we're just starting with an RC delay model for a CMOS inverter. So let me zoom. Oh, that was a lot too much. 250. Okay, so here we start out with our initial CMOS inverter. Our first step was to multiply by 2 the number of transistors that each path has to flow through. So in this case, PMOS is 1 and NMOS is also 1, so it's 2 times 1. So in this case, the pull-up network the value is 2 for K. And in the pull down network, the value is 1. So the next part here is we plug in our 3.8 values, right? So we have capacitance here on the output, right? We have a capacitance on the VDD and ground. We have R over K and 2R over K, right? Now, this non-switching, this capacitance is always tied to VDD. And this capacitance is always tied to ground. Right? So they're never going to switch, no matter what you do. VDD will always be 1 and ground will always be 0. So bye-bye. They're gone. Right, so you have gate, source, and drain. So I've drawn this lower, but this is supposed to be this is the gate. This one is the source here, and this one's the drain for PMOS. And for the NMOS, this is the gate. It's the source. I'm sorry, this is the drain. That's supposed to be the gate. Now it's supposed to be the source. Yeah. So now we have our drains tied together. Our gates are apart, and our sources are never going to change, so we can get rid of these. So you reduce the circuit and you come down here. So we can start adding 2R over K and R over K. And recall that capacitances, you add them in there in parallel. And so you remember there's a difference between how you add them in parallel versus series. So when you add them in series, they're just additive R1 plus R2 plus R3. But in parallel, it's 1 over R1 plus 1 over R2 equals 1 over R total, right? So now we reduce that here to this circuit. So then now these are all on the same node, right? So it means 2, 4, 5, and 6. So in a very convenient method, it just reduces down to R and 6C. So that's why with an inverter, your delay is going to be 6RC. So what did I do here? R over K. Oh, that's right, because K is 2 and this is 1. Yeah, that's right. Never mind. So now we're going to, so that was 2R over 2. This just becomes R. So yeah. So now we have our 3-input NAND gate. So this becomes much more complicated. Okay, so does anybody have any questions before we move on? Okay, so let's zoom in on different parts here, if it ever cooperates. No, I wanted to go the opposite direction. Okay, so first part, same thing, right? We want to determine how many transistors we're going through in each path. So for PMOS, it's 2 times the number of transistors, and for NMOS, it's just K is going to be the number of transistors. So we assign that to each one. So here it's 2, 2, and 2. In this case, it's 3 because you're actually going through 3 transistors, right? So next thing you know, we can plug in our TGO 3.8, and then we see which transistors are going to switch and which ones are never going to switch. So this one's tied. This is the drain here. This is a drain here. This is a drain here, right? And then we have our source here, right? So this is output that's going to switch. This is an output that's going to switch. This is an output that's going to switch. Because they're all tied to the, this is going to be potentially switching, this is potentially going to be switching, and this is potentially going to be switching. Even though they're in series, the key thing is, let's say I need a 0, 0, and 0 to get the path to flow all the way through, right? So if I have 0, 1, and 0, I could have the switch occur here. I can have the switch occur this 0, 0, and 1. I can switch here. Or if I have 1, 0, 0, and I want to switch this, right? It switches here. And then here it's the same thing, that I have it tied into switching because it's tied to the drain. This one is tied to the drain. Let me see if I can, I'm going to attempt to zoom in on this portion again here. There we go. Oops, too far, a little less. Perfect. All right, so in this diagram, I want to differentiate between what a switching capacitance is and what is not. So here, it's tied to the drain. See how it's tied to the output, so it can potentially switch. Right here. So here I have switching, and you can see I have the arrows tied here, here, and here. Right? So then I have, for the pull-up network, all of these non-switching. So this capacitance here is the difference between VDD and whatever this value is. But it doesn't contribute to the switching on the output. It just has the input switching, right? So non-switching, and non-switching. So a lot of these are going to go away. Same thing, 3C, 3C, and then if I scroll down just a little bit, you're going to see the other transistor here. And that's also non-switching. Okay, so does everybody understand now what I'm talking about when I say switching versus non-switching? Should be a capacitance either typically on the drain that's going to eventually contribute to a switching on the output. And the reason why, even though these are series, that these are going to be switching is because you need all 3 of them to be a specific value in order for the Y to be on the output there. So here we're trying to calculate the step response using an effective resistance and effective capacitance by determining which of these contribute to the output switching. So we have some sort of input switch, and we need to figure out what's happening on the output. So let me zoom out from there. Oh, not that far. This is the one compromise when I'm running the team viewer on the other computers that, on the other computers that it's a tad slow. So thank you for bearing with me. Okay, so now we determine the rising and falling. So this is what I was talking about when it's in series. For falling, what I want is I want it to go from a 1 to a 0, right? So I need to, in order for this to be a 0, I need to have anything, it has to go through all of the NMOS circuits, right? So we determined that this switching doesn't apply, that the gate transistors don't apply, and I need all of these to come together, right? So the reason why this is 9C is if we go back to the other diagram, all of those capacitances from the PMOS are there, right? So you can do it. So here the question asks for the worst case and transition from rising and falling. So for falling, the worst case is I need all of them are 1. So I have 1, 1, 1 to 1, 1, 0. So 2 NMOS and 1 PMOS are switching. Right? So in this case, you have 2, 4, 6. Let me zoom in a little more so you can see what I'm talking about. 200 and zoom. So if you look at the switching capacitances here, so you have 2, 4, and 6, and they're in parallel, so they add together, so you have 6C, and then they add with this one. So that's where 9C comes in. So the worst case scenario in this case is I have 3 1s, and I need to switch I switch one of them to get to a 0, right? So I need to start getting them on this output. So when it's 1, 1, 1, that means I put 1s in all the NAND gates, on all the NOR gates, NMOS transistors, I'll get it right eventually, NMOS transistors, so they're all on. So I have a flow from the ground to the output. And the worst case scenario is only one of them is going to turn off, right? Does that make sense why that's the worst case scenario? The best case scenario is all 3 of them switch so it turns off all 3 transistors and it makes life easy. If we've turned on one NMOS transistor, we turn off one NMOS transistor, that means we're also turning on only one PMOS transistor, and we still need that to get from ground to VDD, even though 2 of the PMOS transistors are off and 2 of the NMOS transistors are still on. Does that make sense? I'm starting to see some confused faces. You have a question, Parun? Okay, so this is our worst case scenario in a 3-input NAND gate, right? So we have our 3-input NAND gate up here on the upper left, right? And so our worst case scenario from a 0 to a 1, right? When we have a 0, that means we have a scenario in which all 3 NMOS transistors are on and all 3 PMOS transistors are off, right? So the best case scenario is we switch it from, so where that's working is when they're all 1, 1, and 1, right? So if I just switch them all to 0, what that means is all of these are off, so none of them are conducting, and all of the PMOS transistors are going to be on, so I'm going to have a very strong chance to get from this 0 to this 1 really easily. But so the question I'm asking, and the way it's phrased in the example question, is worst case output transition. So worst case output transition is what happens if I have all of these 1s here. Come on, there you go. I have all of these 1s here, but I only switch it to 1, 1, 0. If it's a 1, 1, 0, it's supposed to switch from a 0 to a 1. So if I switch this one here, what that means is I still have conducting through these 2 NMOS transistors, right? I still have a current flow, and then it gets here and it's supposed to just cut off. Likewise, I'm supposed to have one flow through this PMOS transistor, but these two are cut off, so that strong signal I was talking about when it goes to 0, 0, 0 doesn't exist. So you're fighting a lot of elements within this cell to still get from that 0 to that 1, which is why I've defined it as the worst case scenario. Likewise, if we're going from falling, so I want to get from a 1 to a 0, right? Here. So if it's a logic 1, it can be anything except 0, 0, 0. So in that case, the worst case scenario is I need it to get from 1, 1, 1. If it's 0, 0, 0, right? That means all three of these are off, right? And then all three of these are on. Then what happens if I have 1, 1, 0? I'm switching this transistor and this transistor only, which affects this switching capacitance, it affects this switching capacitance, it affects these switching capacitances. So anything where I'm doing a lot of switching of capacitance requires a lot of power consumption. Does that make sense? Okay, good. I didn't want to move on because I saw a few. I picked up Perun, but I saw I could have easily picked on a couple other people here, right? So that's why we've defined it as for rising 111 to 110, 2 MOS and 1 PMOS. So in this case, 2 NMOS and 1 PMOS. I'm sorry, I'm going to scroll back up. I know people are copying. But we have 2R over K, right? So we define K as 2. So that becomes R, right? So that means we have 1 PMOS and 2 NMOS. So if we look at what I've drawn down here, this diagram is the solution. So here's how we came up with this using the algorithm. We defined K as the value that we need for 2 times the number of transistors we go through the path in PMOS and 1 times the number of transistors we go through in the NMOS, right? So what we have here is we've turned 1, 1 to 1, 0. So we have 2 NMOS conducting and 1 PMOS. So they're switching. So we have 1 PMOS that is switching, right? And then we had 2 NMOS that we have to worry about conduction. This 9C ties in from all the capacitances from the from all of the NMOS and PMOS transistors that are tied to that one output. So we had 6C over here, 2, 4, and 6, and then we have a 3C over here, so that adds up to 9 because they're all in parallel. And then we had R over K. Remember, we defined K as 3 in the second step of the algorithm because we have to go through 1, 2, 3 NMOS transistors. So this is R over 3, 9C, 3C, and 3C. And we don't worry about the other one because it doesn't switch. So instead of R3, R3, and R3, we just have 2 in that case. And the reason why is because if we have 1, 1, 1, then all 3 NMOSs are conducting. We've turned one of them off. And we have 1 PMOS conducting. And now this is our worst case, enabled to get from a 0 to a 1 because we have 2 NMOSs still conducting and we have a PMOS conducting. So does that now make sense why it's set up that way? So that we've defined that as the worst case scenario. So if we had a situation where this was 1, 0, 0, so we have 2 PMOS on and 1 NMOS. So now we've defined this as resistor, resistor. So that's 2 because they're in parallel, right? So this would be R, the R, still 9C. But then we have just one R over 3 and 3C, and then this ties to ground. Does that make sense? So this would be the case if this is 1, 0, 0. And then if it was just all PMOS and no NMOS, resistor, 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 R, 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 9C. And this goes to ground because all of these are off. So now we don't have to worry about the NMOS transistors. So when the question is phrased, come up with the worst case scenario, that allows you to kind of describe, well, what is the worst case scenario? Why is that this case? So if this was an NMOS, it would just be flipped around. So if this, I'm sorry, not NMOS, this is a NOR gate. So NOR gate, the PMOS are in series, right? And the NMOS are in parallel. So in that case, well, let me ask you all, what do you think the worst case scenario for an NMOS transistor would be? Well, before I give the solution, how would you go about trying to figure out what the worst case scenario would be? What would be your first step? Well, how am I defining the worst case scenario? This is a classic case of a lot of engineers overthinking the problem.
Which one is switch?
Switch, and how would I determine when switches occur? Truth table. Yep. So just first thing I'll do is I go 0, 0, 0, oh, no, 0, 0, 0, 1, 1, 0, 1, 1. It's a NOR gate, right? So it's going to be 1, 0, 0, 0, right? Well, this is a 3 input. So you're going to have 1, and then it's going to be a bunch of zeros, right? So it's going to be a 1 on the output when you have 3 zeros. So your worst case scenario is going to be when any of these is 1, right? And you need that 0 on the output. And the reason why is you're still going to have 2 PMOSs conducting. One of them is going to be off, and you're going to have 2 NMOSs off, and you're going to worry about only 1 NMOS being on. And you still need that logic 0 on the output. So that's why this worst case scenario becomes important. So in this case, each path is only going through 1. So instead of K being 3 here, like it was for it's just K is going to be 1. And so it's going to be 2 times K. And that K is going to be 2 times the number. So it's going to be 2, 4, and it's going to be 6. And so if I go down to the next one, so if we were to do that, you can then use that same algorithm to figure out a 2-input NOR gate. And then you would eliminate, so the non-switching would be the ones that are tied to your gate and your VDD, right? But then you would still have, in this case, you see how here on the NMOS, it's the ones that contribute are still there, and this one went away. So we had, I'm sorry, this was 9C, but these are 3C, 3C, and 3C. So you'd have, in this case, you'd have resistor 6C, 6C, and then in your third one here, it would be 6C plus 1, 2, and 3 for your NMOS, right? So that becomes 9C again. Right. So I'm just debating whether or not I should. No, this next concept will require an entire lecture. So let me dismiss you now. Do the TGOs examples 3.1 through 3.3, and let me find the last 3.9. And also Friday by 5 p.m. have to me your rough draft of your write-up.
Roughly how long do you want that?
Just look at the sample write-ups. It should be a couple of pages in single space. I mean, the key thing is you read it over. The keynote I want you to do is you want to give your own personal description of what's going on in the article. So this is described by why you think this is interesting. If there are concepts you don't understand, look them up. Describe how they tie into. Once you see the concept that you've looked up, go, oh, this is something I learned, or we learned through the process of researching that this meant X, and therefore that's actually really interesting. And then it should be kind of exciting. And then I'll help you fine tweak it before it would go online or anything like that.
So we should put like personal. Why we think it's interesting.
Yes. Why does this topic excite you when you first saw it? And what more you learn? And so remember, make this the last note, and then I'll dismiss you. When you all are presenting this, I don't want you to be bored. Just go presenting this, stupid. It's something else that no one in the class knows yet. You're finding something that's outside of the scope of me just droning on over the notes, right? So it should be something that you all found something that was really interesting, and as part of it is conveying what you find interesting, but being able to make sense to everybody else in the class. So the key is the most important thing is find that thing that excites you about it. Once you find that thing that excites you, you'd rather listen to somebody who is excited about it rather than bored out of their mind, right? So I don't want you to be bored out of your mind. So write your article in that vein. Any other questions?